Okay, hello dear friends. Let's read some numbers. Numbers at their most elementary are just adjectives describing quantity. We might say, for instance, 3 chairs or 2 sheep. But even as an adjective, we understand instinctively that the phrase 2.5 goats makes no sense. Numbers, then, can have different uses and meanings. As ancient people used them in different ways, numbers acquired symbolic meanings, like the water lily that depicts the number 1000 in Egyptian hieroglyph. Although aesthetically pleasing, this visual approach does not lend itself to algebraic manipulation. As numbers became more widely used, their symbols became simpler. The Romans used a small range of basic signs to represent a huge range of numbers. However, calculations use large numbers were still complicated. Our modern system of numerals, is inherited from the Arabic civilization of the first millennium AD, using 10 as its base. It makes complex manipulations far easier to manage. That's a good way of learning to read. Natural numbers, 自然数. Natural numbers are the simple counting numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. The skill of counting is intimately linked to the development of complex societies through trade, technology, and documentation. Counting requires more than numbers, though it involves addition and hence subtraction too. As soon as counting is introduced, operations on numbers are also become part of the lexicon. Numbers stop being simple descriptors and become objects that can transform each other. Once addition is understood, multiplication follows as a way of looking at sum of sums. How many objects are in 5 groups of 6? while division offers a way of describing the opposite operation to manipulation, to multiplication. If 30 objects are divided into 5 equal groups, how many objects are in each? But there are problems. What does it mean to divide 31 into 5 equal groups? What is 1 take away 10? To make sense of these questions, we need to go beyond the natural numbers. 所以就有了小数、分数、复数。1. Together with 0, the number 1 is at the heart of all arithmetic. 1 is the adjective for a single object. By repeatedly adding or subtracting the number to or from itself, all the positive and negative whole numbers, the integers, can be created. This was the basis of tallying, perhaps the earliest system of counting, whose origins can be traced back to prehistorical time. 1 also has a special role in multiplication. Multiplying any given number by 1 simply produces the original number. 任何数乘以1都是1。This property is expressed by calling it the multiplicative identity. The multiplicative identity. The number 1 has unique properties that mean it behaves in unusual ways. It is a factor of all other whole numbers, the first non-zero number and the first odd number. It also provides a useful standard of comparison for measurements. So many calculations in mathematics and science are normalized to give answers between 0 and 1. Zero is a complex idea, and for a long time there was considerable philosophical reluctance to recognize and put a name to it. The earliest 0 symbols are only found between other numerals, indicating an absence. The ancient Babylonian number system, for instance, used a placeholder for 0 when it fell between other numerals, but not at the end of a number. The definitive use of 0 as a number like any other. The earliest definitive use of 0 as a number like any other comes from Indian mathematicians around the 9th century. Aside from philosophical concerns, early mathematicians were reluctant to embrace 0 because it does not always behave like other numbers. For instance, division by 0 is a meaningless operation, and multiplying any number by 0 simply gives 0. 任何数乘以0都等于0，任何数除以0都不成立。However, 0 plays the same role in addition as 1 does in multiplication. It is known as the additive identity. Additive. Because any given number plus 0 results in the original number. What a funny thing, n'est-ce pas? 0. Infinity. Okay. Infinity represented mathematically as this infinity sign is simply 无限 is simply the concept of endlessness. An infinite object is one that is unbounded. It is hard to do mathematics without encountering infinity in one form or another. Many mathematical arguments and techniques involves either choosing something from an infinite list or looking at what happens if some process is allowed to tend to infinity, continuing towards its infinite limit. Infinite collections of numbers or other objects called infinite sets are a key part of mathematics. The mathematical description of such sets leads to the beautiful conclusion that there is more than one sort of infinite set, and hence there are several different types of infinity. In fact, there are infinitely many bigger and bigger kinds of infinite set. And while this may seem counterintuitive, it follows from the logic of mathematical definitions. Infinity. I think I can do an infinity loop. Let me do it right here, right now. So I have a number . If I tape it here, it's too short. Let me cut a longer piece of paper. this one is not infinite because you can circulate, and this one the infinite loop, isn't it? So your hand goes with the edge, and it continue, and there is no end. This is not the infinite definition in mathematical term, maybe, but it is infinite. Infinite number system. The next one is number system. Gosh, we are on decimal binary. Number system. A number system is a way of writing down numbers. In our everyday decimal system, we represent numbers in the form 434.15, 434.15. For example, digits within the number indicate units, tens, hundreds, tenths, hundredths, thousands, and so on, and are called coefficients. So 434.15等于4乘以100加上3乘以10加4乘以1加1/10加100/5. This is simply a shorthand description of a sum of powers of 10, and any real number can be written in this way. Any real number can be written in this way. But there is nothing special about this base 10 system. The same number can be written in any positive whole number base n using coefficients ranging from 0 up to 0 up to n 减1, n minus 1. For example, in base 2 or binary, the number 8又15/5 can be written as 1000.0101. The coefficients to the left of the decimal point show units, twos, fours, and eighths, powers of 2. Those to the right show halves, quarters, eighths, and sixteenths. 2/1, 4/1, 8/1, 16/1, 32/1, 64/1, 128/1, 256/1, 312/1, 624/1. Yeah. Most computers use the binary system since two coefficients, 0 and 1, are easier to work with electronically. Since two coefficients are easier to work with electronically. decimal 0123456789010101212The number line. The number line is a useful concept for thinking about the meaning of mathematical operations. It is a horizontal line. Okay, I need to stop it.